All right, it's 9:02 a.m. Welcome, everyone. Thanks for bearing with us for just a couple minutes here. My name is Aaron Timmons. I'm the Mathematics Content Director for Advanced Kentucky. I'm joined today by Michael Marshall. He is our Advanced Kentucky Access Algebra Program or Content Manager, and our presenter for today, Melanie Gray from Madison Central High School. Welcome to week 3 of our AP online review sessions. Today we're focusing on Unit 7, which would be differential equations. I'll let Melanie talk about herself here in a little bit. But we're just going to go over a few housekeeping procedures and then we'll get started. All right, so this review session is intended for a Kentucky audience. We welcome every teacher, student from around the state that can join us. However, we do realize that there's people from beyond Kentucky, outside of Kentucky, that are here. So you are also invited, and we are glad you can be with us. Please remember, though, that any participant causing a disruption to the session will be removed, and make sure you understand those terms. Our contact information is all here on the screen for Advanced Kentucky, as well as myself and Michael. Feel free to reach out to us with any questions you have. Follow us on Twitter, Facebook, all of the above. Your microphones will be disabled for the duration of this session. Your video, we ask that you remain off. If it comes on, we will shut it off or remove you. Please use the chat feature in the bottom right corner of your Zoom screen. Any questions you have at all for us, regardless if you are a teacher or student, please put those in the chat box. Michael will be monitoring along with myself, and we will be asking those live to Melanie, who can give you her feedback. Also, if you don't feel comfortable posing a question to the entire group, you can chat directly to any of the three of us, so please make sure you take advantage of that as well. Please make sure you visited kyap2020.com. That's where you can find today's handouts, as well as upcoming sessions, and other resources for both teachers and students. Past recordings will also be posted here as well. So before we begin, I'm going to pause the recording here for about 3 minutes. I'd like you all to go to this bit.ly link here, open up a new browser. It's a very quick 4 or 5 question Google form just to fill out so we can keep track of who all is here. And then you can go ahead and make sure you got the handouts in front of you. If you need to test the chat, make sure that's working. If you don't hear us, I know you can't hear us, but you need to make sure you click join audio, so figure out a way to communicate that to your friends if they're expressing that difficulty. But hang tight for about 3 minutes and then we will get started. All right, so again, hopefully you've had the chance to sign in. We are going to turn things over right away to Melanie Gray. She can introduce herself, tell us a little bit about herself and her AP experience, and then we will get right started. So Melanie, it's all yours.
All right. Hi guys, I just wanted to welcome everyone. I'm super excited to see everyone here today. I just wanted to thank you, first of all, for being here. While I am queuing up my screen, if you guys want to, you can drop your name and your school in the chat box for me. Just, I see some of my students on here this morning, but I would love to know where everyone is from. If you don't mind to just write your name and your school in the chat box. We'd love to hear from you. And while you're doing that, I'm just going to tell you a little bit about myself. For those of you that don't know me, my name is Melanie Gray. I teach at Madison Central, and then I also adjunct for Eastern Kentucky University. This is my 19th year teaching, and I have a strong love of calculus, so I'm so glad that you guys are here with me today. The session that we're covering today is differential equations. We're going to talk a little bit about that today, review, but also I realize there's some of you that may not have gotten a chance to learn about differential equations prior to all these NTI days. So we'll take some time going back over some of the basics, and then we'll finish the lesson by looking at some free response items. So this is content review session number 3. If you didn't get a chance to log on for 1 and 2, you can go back and watch those. Those are recorded. And then next week, Mr. Brock Strickland will be back for some free response strategies. So make sure you check that out, same time, same place. And then I believe, Aaron, correct me if I'm wrong, I believe Tony Record's going to be here on the 5th, and
That's
he will
right.
also be doing some free response strategies. For those of you that don't know, Tony Record is the one doing the BC College Board lives right now, and so both Brock and Tony will have excellent lessons for you these next 2 weeks, so make sure you tune back in. Then the agenda for today, right now we're kind of doing the introduction and the overview. I put a review of general and particular solutions, but again, we're going to start off with some of the basics, especially for those of you that may have never learned about differential equations before, and then we'll wrap it up by taking a look at some past free response items dealing with differential equations. So now I'm going to share my handout screen with you. If you didn't get a chance to print off the handouts, you can certainly go on and do that, but I would like for you to have some pencil and paper out, working along with me as we work through the handout today. Just making sure, Aaron, you guys see in my iPad screen okay?
Yeah, we're good.
Yeah, okay. All right, so like I said, today we're talking about differential equations. We're going to start out with some just very basics to give you an idea and review that with you, or maybe even teach you a little bit if you haven't seen it before. We are going to look at the calculator for just a little bit once we get through this first page. But then, like I said, we'll wrap up with some free response questions that I think will really help you. So first of all, you'll notice on your handout, it says a differential equation is an equation that relates one or more functions and their derivatives. So in that gray box there, I just gave you some examples so you can get the big picture of what a differential equation might look like. So you'll notice several different examples in that gray box there. We've got dy by dx equal to y. You'll notice the y double prime plus y equals 0. And then that third option is dA by dt equals 2.1 minus 3a over 200. So some different variables there. And then the last one, dy by dx equals x over y. So this just gives you an idea of what a differential equation looks like. And then I also wanted to start off by sharing with you the free response question from back in 2012, because I thought this would give you a good idea of an application of a differential equation so you can get that pictured in your head. So let's look at 2012. It was number 5. The rate at which a baby bird gains weight is proportional to the difference between its adult weight and its current weight. At time t equals 0, when the bird is first weighed, its weight is 20 grams. If b of t is the weight of the bird in grams at time t days after it's first weighed, then dB by dt equals 1/5 times the quantity 100 minus b. So it says let y equal b of t be the solution to the differential equation above with initial condition b of 0 equals 20. Again, I just wanted to share that with you so that you could kind of see a differential equation in context of a problem, and you would get the big picture of what we're dealing with differential equations. And then hopefully if we have time at the end, we can come back and maybe solve this free response question if we have time. And if not, I'll challenge you guys to solve this one after today's lesson. Okay, so on your handout, we have a solution to a differential equation. Could be one function or it can be a set of functions. So just some vocab here. If it's one function, we call that a particular solution. So if you have the handout to fill in, you can fill in the blank there with particular. Or it could be a set of functions called a general solution. So I wanted to give you an idea of what those would look like. So we've got this table here in the middle of the page. We're going to just do a short little list of some general solutions. and then some corresponding particular solutions so that you could see what that would look like. Again, this is just kind of big picture stuff so that you can get your mind around what we're solving and dealing with today. So one example of a general solution would be the function y equals x cubed plus 5x plus c. So just a cubic, and then notice that plus c where c stands for a constant. And then the particular solution that corresponds to that might be something like y equals x cubed plus 5x minus 2. Excuse me. So the general solution is a solution. You can almost think about it as like a parent function, and that can have a vertical translation, so that c value shifts your general solution up or down based off of the initial condition. Another example might be something like y equals c e to the negative 2x. So again, notice that c value, which stands for a constant, and then the particular solution to go along with that might be something like y equals 20e to the negative 2x. And then we'll do one more. The last example of a general solution might be something like y equals plus or minus the square root of x squared plus c. And then an example of a particular solution that would correspond to that general solution would be something like y equals the negative square root of x squared plus 4. And again, the particular solution would be based on an initial condition or a point that the graph passes through or something of that nature. So now down at the bottom in example 1, we're going to look at something called a slope field. And so I've given you a very simple example in that I wanted you again to see the relationship that exists between a differential equation, the slope field, and then also the original function, the function y equals f of x. So let's just start by sketching a slope field for the differential equation dy by dx equals 2x minus 2. So to sketch that slope field, what we're going to do is I would like to just start here at this point, negative 3, 3. Doesn't really matter where you start. I'm just starting in the upper left-hand corner. And I'm going to evaluate that slope, dy by dx, at the ordered pair negative 3, 3. So to do that, we substitute into our dy by dx, our slope, or y prime, if you want to think of it like that. 2 times the x value is negative 3 here, minus 2. And that's going to give you negative 8, a slope of negative 8. So what you want to do is draw a little line segment through that point and estimate a slope of negative 8. There's a couple of different ways you can do that, but one way is you can think about a slope of negative 8 that's going to pass through this point here. I'm just highlighting this point for you. And then if I imagine going down 8 units, so 1, 2, 3, 4, 5, 6, I'm going to go off the graph, 7, 8, and then write 1, and I'm going to put a little point down there. And so I'm going to highlight these 2 points. And I want you to imagine a line going through those 2 points. Now we're not going to draw a line, but we're going to draw a little line segment through the point negative 3, 3. And we want that line segment to have a slope as close to negative 8 as we can get it by eyeballing it. So again, it doesn't have to be perfect. You just want to try to draw a little line segment and envision that line segment extending through the other point that I've highlighted down there at the bottom. So that's our first segment. And then if we want to move down to the point negative 3, 2. So I'm going to take those off for just a second, and then I'm going to now highlight the point negative 3, 2. Well, notice that if we do this substitution again, so dy by dx at -3, 2, well, the differential equation, this differential equation only deals with x. So for any point that has an x value of -3, no matter what the y value is, we're going to have a slope of -8. So we can use that pattern or that idea to go ahead and fill in all of our segments where x is equal to -3. So you're going to try to mimic that slope and just eyeball it. You don't have to really draw out the points every single time, but you just want to eyeball it and try to get as close to a slope of -8 as you can. And again, I'm filling in all of the x values of -3 because this particular differential equation only deals with x. It's 2x minus 2. As you notice up above in my other examples, you'll see that for, depending on the differential equation, you might have to sub in x and y. But for this one, we're just subbing in x. So we can actually fill in the slope field fairly quickly. If we move on to our next point, which I'll highlight here. So let me erase this one, and then I'm going to highlight this next point that we're looking at. And so that point is going to be the point -2, 3. So now when I substitute in -2 for x, I get 2 times -2, which is -4, minus 2 gives me -6 this time. So I want a slope of -6, so I'm going to go down 6. So 1, 2, 3, 4, 5, 6, and write 1. And I'm going to highlight that point so you can kind of see it. And then we're going to try to draw a segment that has a slope that would pass through those 2 points. And as you can see here, I'm going to go ahead and fill in for all of my x values of -2. As close to a slope of -6 as I can get. Now, again, I don't want to give you the impression that you can always just check the top point and then fill in underneath. The only reason that I can do that on this one is because my dy by dx is dependent upon the x value only. That will not always be the case. So let's continue on here and find our slope when x equals -1. If you feel confident, drop in the chat box what you think the slope will be when x equals -1. Hey, I see some good responses. Thank you guys for participating. -4. Great. Awesome, awesome, awesome. Thank you all. So -4, I'm going to look at this point here. And again, I'm going to go down 1, 2, 3, 4, right 1. And I'm going to highlight that little point to kind of give me just a reference there. And try to draw a line segment that would pass through those 2 points. And mimic that all the way down where x equals -1.
Now, Melanie, I got a question.
Okay.
What would it look like if only the y value was given?
What would it look like if only the y
instead
value?
of
Do you
2,
in the y by dx?
Like if it, yeah, let's say it was 2y minus 2.
So in that case, if it were 2y minus 2, then our dy by dx would be dependent only on the y value. So in that case, you could, let's say we started over here at -3, 3. Then you would take that slope and then all of these. Can you guys see my pointer on the screen? Or no? You can see
Yes.
the pointer?
Yes.
Okay. Then all of those would be the same. Is that what you were asking, Mike? Or someone was asking, do you think I answered that okay?
I
Or do you
do.
have anything to
Briefly
add?
say, I think that, yes, that's what they want. Tell them what they would do if it was an X and a Y.
So if it were an X and a Y, we would have to substitute in both the X and the Y into the dy by dx. And there could still be patterns there, but you would want to make sure that you take both the X and the Y and substitute. Like if it were something like up here in the gray box, this last example, dy by dx equals X over Y. In that case, you would have to substitute the X and the Y. Awesome. Okay. So now let's finish out this slope field. Moving on to where we have X equals 0. So if you sub in 0 there, you know that you're going to get 2 times 0 minus 2, which is -2. So envision your line passing through those 2 points and try to get a good, notice how our slope is flattening out a little bit there. I may have flattened that one a little bit too much, but I'm eyeballing it. So again, just try to do the best you can as far as your slope field is concerned and your slopes.
And then Melanie, I had a question.
Yes.
So I realized that students will probably not have to draw a slope field on this year's exam simply because of the format. But I was wondering
Right.
if you and Michael, being experienced AP exam readers, could talk a little bit about what you all are looking for as a scorer when students do a slope field.
So usually, now I haven't graded a differential equation problem on the exam and the actual exam before, but I have, in mock exams and that sort of thing. But from my understanding, most of the time we're looking for the 0 slope, and that will usually earn you a point if there's a 0 slope. And then for the second point, just like the overall field. Michael, have you graded one of the slope field problems at the reading before?
I can't remember if it was at the reading or a mock, but you're right. You're not going to have this many points. You'll have like 9 points maybe. And
Yes.
then it's not that they're taking a ruler and checking the steepness. It's in relation to everything else. So if one is less steep, it should look less steep. If they supposed to be the same, they should look the same. But it's
Yes.
usually worth about 2 points, one for the zeros, one for everything else.
Good. Yes, thank you.
And then
All
you
right,
you don't want to draw a segment where there's not a dot indicated. You want to stay over.
Yes.
Yes.
Very true. Very true. So when we look at some free response items, I think one of them that we're going to look at today, there may only be like 6 points. So Michael's correct. There, I think 6 to 9 points is usually pretty consistent what you see. And then, as Aaron pointed out, definitely if there's not a dot there, you don't want to draw anything where there is not a dot. Okay, so moving on to the next one, when X equals 1, then here's our 0 slope. And the 0 slope, usually if it is a slope field problem, that earns you that one of the 2 points. So for a 0 slope, you want to make sure that you put your horizontal segment there. And then on the other side, when X is equal to 2, then we know we have a slope of 2 again. So I sort of use symmetry. I knew that I had -2 over here on the y-axis. So I tried to use symmetry to kind of mimic that slope on the other side. And so we can go ahead and fill in all of these X values of 2. And finally, the last one, if we substitute in 3, we're back to 4. And so I can try to mimic symmetry again with X equal -1 there. but we're going in the positive direction, of course, so we should have increasing segments. All right, so looking at that slope field, this brings us to our first poll question. Erin, if you don't mind to pull that up. I just want you to look at the, this should only take about, I don't know, 30 seconds. If you look at the differential equation, 2x minus 2, think about that as your dy by dx or your y prime. And looking at that slope field, my question for you is the function y equals f of x is from what family? Do you think the y equals f of x is a linear function, a quadratic function, a cubic function, or an exponential function? And so I'll give you about 30 seconds or so to respond. I've got a lot of answers already there. Okay, let's give you about 5 more seconds.
Sorry, I cut you off a little bit early.
Oh, okay, that's all right. Okay, now, can you guys see the results, or do I need to share those?
They can see them.
Okay, perfect. So looks like, so quadratic was the correct answer. Looked like several people answered linear, which I'm guessing that you were probably thinking about the dy by dx. You were thinking of y prime instead of y. But if not, you can drop in your chat box maybe what your misunderstanding was. So it is going to be a quadratic, and if you look at the slope field, you can think about that slope field and the differential equation as a set of directions telling you how to sketch your curve. And your slope field, think about those as all of your general solutions. So it's going to be a vertical translation of all of the general or all of the particular solutions. So, and they're dependent upon which through as to which translation you're going to pick. So I may have to share my screen again. Let me see if it's still, yeah, I'm gonna have to share this again. I found that if I talk too much, my screen goes to sleep on me, so I'm gonna have to reshare it with you. There we go. So let's say that we have, I'm just going to call this y prime, but it's dy by dx is 2x minus 2. Then to find out what y would be, this is why I picked this particular differential equation, is because you can find this one really easily by thinking about, okay, what function would we have to take the derivative of, or set of functions that we would have to take the derivative of to get the slope of 2x minus 2. So if you feel like you know what that y function is, you can drop it in the chat box for me. I see some responses coming in. X squared plus 2, or x squared minus 2x plus c, x squared minus 2x. X squared minus 2x plus c. So really good job, guys. Thank you for participating. And yes, I agree. Your y function could be, it could be x squared minus 2x. But we're going to say x squared minus 2x plus c, and that's going to take care of what we call our general solution. And then an example of a particular solution would just be to give a specific C value. So for our particular solution, we could choose something like x squared minus 2x minus 4. And that would be dependent upon, like I said, which point that you want to pass through, or an initial condition or something of that nature. Now, I did want to take a minute to show you on the Inspire how you can sketch a slope field. Now, the 84, to my knowledge, doesn't have a built-in capability for those of you that use an 84, it doesn't have a built-in capability for doing slope fields, but I know there's a program you can download if you have an 84. But I'm going to now share my calculator screen with you. I just think this is really neat to see the slope field on the calculator. So I want to show you how to do that. So this is on an Inspire. I'm going to insert a graph. And the first thing I'm going to do is I'm going to change my window settings to be the settings of
Melanie,
the
we
slope
don't
field.
see your screen just yet.
Oh, you don't see it? Oh dear. Okay, let me try it again. How about now?
Yes. We do.
Yes.
You got it? Okay. I'm sorry about that. All right, so what I did is I just inserted a graph, and then I came over here and I'm currently changing my window, and I'm changing the window to match the slope field that we just drew. So we're going from -3 to 3 on a scale of 1. And then I'm going to come here to the graph and the entry edit. And typically we enter a function, but I'm going to come down here to differential equation. And I'm going to type in our differential equation. So 2x minus 2, I believe it was. And then when I hit enter, you'll see that beautiful slope field that we just sketched. Isn't that gorgeous? Love it, love it, love it. So you can see that, and then I went ahead before the session started, and I typed in several transformations of that original function, x squared minus 2x plus c, so that you could see the functions, or several of the functions, alongside of the slope field. So you can see that quadratic behavior, and then you can see all of these different translations of the general solution. So Aaron, here's our next poll we're going to put up. And so the question is, which of the following functions is the solution to our differential equation with an initial condition of y of 0 equals 1? Y of 0 equals 1. So the blue graph here is the F1. Notice the name is underneath. And then F2 is the graph in red. And then F3 in pink. And then, or I'm sorry, F3 is in black, and then F4 is in pink. And then F5 is down here in green. So the initial condition is the point that we're passing through. Take just a couple more seconds if you haven't responded. Okay, so looks like that the majority got this one. Great job. F2 was the answer. It's this red. I'm going to stop sharing this so that I can see the screen, hopefully. Okay, yes, this red function here, the F2 is the function that's going to pass through the point 0, 1, which was the initial condition. So that would be our particular solution given the point 0, 1. You can also draw the slope field on, you know, I could go up here and I could insert a slope field by going to graph, entry, edit, and then going down here and doing a differential equation on top of this so you can actually see the slope field along with the graphs. There we go. A little slow, but now you can kind of see how if you were asked to draw a slope field, you would, I almost think about these as like little bumpers. You use these as a guide, your slopes as a guide of how to sketch that curve. The one last thing I wanted to say about the calculator, even though, like Aaron said, this it's not likely they're going to ask you to draw a slope field on this year's exam, but the one other thing I wanted to share with you about the calculator is if you are typing in to the Inspire a differential equation that has a y, then you're going to need to specify, if you just typed in like x over y. So let me do a new document here. If I were going to insert a graph and then do another slope field, but I wanted to do x over y, if you just simply put in x over y, it's not going to give you the slope field for that. You have to, since this is defined as y1, you actually have to do x over y1, and then you can see the slope field for that particular function. If you were typing it into y2, you would have to use y2 and so on. Okay, so moving on, let's, oh my goodness, I'm super short on time, so I'm gonna skip ahead to some of the free response questions. Let's see here.
And then Melanie, while you're pulling that up, again, Monique mentioned the TI-89s. If you all use those, they can do slope fields in pretty much the same way you described. So those of you that don't have Inspires but have 89s can do that. And then again, there is a program like you mentioned that you can download for slope fields on the 84.
Okay, let's move on down to looking at some actual free response and actually solving some particular solutions and general solutions. So to solve for a general solution, we always say that we separate, we integrate, and then we solve for y, or whatever the dependent variable might be. Let's focus in on the particular solutions because I am so short on time, and get into some of the free response questions. So if you're solving for a particular solution, then what you want to do is we're dealing with some separable equations here. And I'll show you, when we get down to the free response, I'll show you that those equations typically involve both the x and the y. But just so you have the notes for a particular solution, think about it as you're going to separate, you're going to integrate, then you're going to find C, and that's by using the initial condition. And then we're going to solve for y. Or whatever your dependent variable may be. So I'm going to skip through my examples, my generic examples, and I'm going to move into the free response questions. Now, I will post the solutions to this handout today. So if you want to work through the generic examples on your own, you can go back to the handouts and sort of check yourself. So we've talked about slope fields today. Part A is sketching a slope field. So we're gonna, I'll leave that one for you to try on your own. For part B, I want to point out that it's asking you to, let's actually work part B and part C together. Part B says, let y equal f of x be a particular solution to the given differential equation. It has initial condition f of 2 equals 3. Now this is asking us to write an equation for the line tangent to the graph of f of x at x equals 2. So we've got this initial condition f of 2 equals 3. We want to write the equation of the line tangent to the graph. So remember, this is writing the equation of a tangent line, and you can start by using point slope formula. So let's start with y minus y1 equals the slope times x minus x1. And then usually I'll come over here to the side and I'll identify what each of those variables stand for. So my x1 is going to be 2, my y1 is going to be 3. And then for my m, I'm going to use the dy by dx, that's just my slope, and I'm going to evaluate it at the point 2, 3. So here's what we were talking about earlier when we were doing the slope field. Notice how this differential equation has both an x and a y. So you're going to have to substitute in both to figure out what your slope would be at that point. So I'm going to put in 3 and square it for my y, 2 in for x, and it looks like my slope turns out to be 9. So then I come back over here and I sub in my 3 for my y sub 1, my 9 for my slope, and then my 2 for my x sub 1. And then I'm going to go ahead and move that 3 to the other side. It's not necessary to get it in slope intercept form, but the reason I'm going to move that 3 to the other side is because the second part of this question is asking us for f of 2.1. And so here's my equation of the tangent line, but then when I evaluate f of 2.1, I'm just going to substitute into that equation we just came up with. And once I substitute in, I'm going to walk away from part B. It's not necessary to simplify, so we're going to leave it as 9 times 2.1 minus 2 plus 3, and we're going to get the point for that. Then moving on to part C says find the particular solution. So I know sometimes when students see that word, that phrase particular solution in part B, they jump straight into finding the particular solution. Be very careful about that. Make sure that you know what the question is asking you. In part B, it does ask us to write an equation of the tangent line. So part C is where we're going to jump into finding the particular solution. And that's where we're doing what we call separate, integrate, find C, and then solve for y. So looking at this differential equation, it was y squared over x minus 1. So I'm going to write this as dy by dx equals y squared over x minus 1. And so the first thing that you want to do is to separate your variables. So you want to get everything involving a y on one side of the equation and everything else on the other side of the equation. So all of your x terms on one side and all of your y terms on the other side. So if I separate these equations, notice that you have a y squared on top of the right-hand side. So I'm going to move that to the left-hand side, and it goes to the denominator. But I'm going to write it as 1 over y squared dy. And then that x minus 1 stays in the denominator of the right-hand side, but I'm going to move the dx from the left-hand side. Now, it looks like we're multiplying. We're not actually using multiplication, but that's how it works. That's how you can sort of think of it. So if the dx is on the bottom, you can move it to the other side, to the top, or I like to move it out to the side. Because after you separate, which is what we've done here, and we've earned our first point, then the next step is to integrate. So if we're going to integrate both sides, then when you integrate the left-hand side, don't forget that 1 over y squared, you can write as y to the negative 2 power, and then we can use that reverse power rule where you add 1 to the exponent and divide by the new exponent. So here we have negative y to the negative 1 on the left-hand side. You add 1 to the exponent, divide by the new exponent. On the right-hand side, notice how that is, you can think of that as u prime over u or 1 over u. Think about u substitution if you want. But it is natural log. Antiderivative of 1 over x minus 1 is natural log of x minus 1. And then we do have to add a constant. So you might be thinking, well, why didn't you put a plus c on the left-hand side? Well, technically, we do have a plus c on both sides. But remember, if you add a constant to a constant, or even subtract a constant from a constant, you still just have a constant. So it's only necessary to add c to one side, and I usually add it to that right-hand side to get ready for this next step. So we've separated, we've integrated. Our next step is to find c. And to find c, we have to use that initial value and substitute it in for our x's and our y's, or our x and our y. So I'm going to rewrite this as negative 1 over y, but y was 3 from the initial condition here up top. Then my x was 2, and I'm solving for c. So notice here the ln of 2 minus 1. Well, we know that 2 minus 1 is 1. Absolute value of 1 is 1. And of course, ln of 1 is always 0. So that makes our c value negative 1/3. Now I'm going to substitute that c value back into this very first step after we integrated. And so I'm going to write it as negative 1 over y instead of negative y to the negative 1 equals ln of absolute value of x minus 1 minus 1/3. And now I need to solve for y. I need to get y by itself. So to get y by itself, the first thing I'm going to do is multiply everything by negative 1 to get rid of that negative on the left-hand side. So this becomes a negative ln of x, absolute value of x minus 1 plus 1/3. Then to get y, I'm actually just going to take the reciprocal of both sides. So the left-hand side becomes y over 1, or just y, and the right-hand side becomes 1 over the negative natural log of x minus 1, and that's going to be plus 1/3. So I believe that was worth let's see, I think it was worth maybe 6 points. You get a point for the separating, and then 2 points for the integrating, a point for the constant of integration, and then a point for using the initial condition, and a point for your final answer, the y value. So I'll share that. Oh, it was only 5 points. I'm sorry. You only got this particular question. You only got 1 point. You had to have both the constant of integration and using the initial condition. Some years they'll give you a point for each of those. But yeah, this year it was only 5 points. And then notice you get a max of 3 out of 5 if there's no constant of integration. And then you get 0 out of 5 if there are no separation of variables. So I know I'm running short on time, Aaron. Do you have?
I know we're right about 3 minutes from the top of the hour. So I know we started a little bit late. I didn't know, Melanie, if you'd be interested in just hanging on and working an additional problem. Those of the participants that need to leave can, and we'll still continue this recording, and we'll post the full recording to our website afterwards. But if you want to take time to work one additional problem so they can see one more, you are welcome.
That would be excellent. Thank you so much. Yes.
So we're going into
I would
overtime.
love to do that. Yeah, overtime. Here we go. All right, so let's look at, let's go back. Why don't we look at maybe 2018? So this is going to be the last one in your packet. You can see here in part A, they're asking you to sketch 2 slope fields. Again, it's not likely, I don't think that they would ask something like this, since we are going to have to answer on our own paper this year. So let's skip on down to part C, which is finding the particular solution. And on part C, we have an initial condition of 1, 0. So we have dy by dx equals 1/3 x times y minus 2 squared. And so again, the first step is to separate your variables. So I'm going to leave that 1/3 and the x on the right-hand side. I'm going to move my y minus 2 squared to the left-hand side with my dy. And the dx, I'm going to move to the right-hand side. It was on the bottom, so it comes up beside the 1/3 x. So we earn 1 point for that separation. We've separated and gotten all of our y's on one side and our x's on the other side. And now we're going to move into integrating. So I'm going to integrate both sides. You can use substitution here if you like, or you can think about this as y minus 2 to the negative 2 power. And since that chain rule, when you think about the derivative and the chain rule, you chain on a 1 anyway. It's already sort of in a form that's easy to work with. So our antiderivative is going to be negative y minus 2 to the negative 1 power. And then on the right-hand side, we're going to have 1/3 x squared over 2, but I'm going to multiply that times 1/2 instead of dividing by 2. So I can multiply that times the 1/3, and then don't forget your plus c. Then at this point is when I figure out what my C value is by making my substitution of the initial condition here. So I'm going to sub in -1 over y value is 0 minus 2 on the bottom. So again, I change this back to -1 over y minus 2 instead of writing it as a negative exponent. And on this side, I get 1/6 times 1 squared plus c. And so I have 1/2 equals 1/6 plus c. And then you can think about that 1/2 as 3 over 6. Subtract off the 1 over 6, and that gives you 2 over 6, which reduces to 1/3. Now, once you find your C, you're going to substitute it back in to -1 over y minus 2 equals 1/6 x squared plus 1/3. Now we have to get y by itself. Solve for y, our last step. So I'm going to start by multiplying through by a negative. And I'm also going to change this to 2 over 6 so that I can write this as one big fraction. So it's going to look like -x squared minus 2 on top all over 6. And the reason I got that common denominator there is because an easy way to get y by itself is now just to take the reciprocal like we did on that last example. So take the reciprocal of the left-hand side, you get y minus 2. When you take the reciprocal on the right-hand side, you get 6 over -x squared minus 2. And then to get y by itself, we move the 2 to the other side. And we end up with 2 plus 6 over -x squared minus 2, or some version of that answer. You may have simplified a little bit differently and written this a little bit differently, but that is one version that would earn you that point. And then I'll share with you that scoring guide as well. And you can see this particular year looks like you got 5 points for part C as well. And their solution, they factored that negative out to the front, but we get the same thing overall. All right, Aaron, I think that's all for me. But can I say one thing though before I log off?
Absolutely.
I just wanted to again thank the students for coming today, and I hope that you guys will come back next week and the week after that, and I hope we're doing this for you. And having said that, just a big shout out to Advanced Kentucky, because we are so fortunate to have you guys to support us and to support our students during this time. So thank you.
Well, thank you, Melanie. And like I said, Advanced Kentucky would not function nearly as successfully if we didn't have good teachers and educators such as yourself. So we appreciate you taking your time to share with us your expertise on differential equations today. I know that that's usually a big topic that can be intimidating to students. So having you walk us through it was very much appreciated. All right, let me go ahead and share one more thing. All right, so here's just a recap of what we did today, as well as contact information for us. So if you have questions for Melanie, Michael, or myself, feel free to reach out to us. If you need the handouts, again, there's the link to it. This recording will be posted to kyep2020.com by the end of the day. Next week, we're joined again by Mr. Brock Strickland. He was with us last week. He'll be going over free response strategies as well as a mixed review of the entire course. And then, like Melanie alluded to, on May the 5th, we're joined by Mr. Tony Record, who will be doing preparation really geared towards what this AP exam this year is going to look like. So both of those, highly encourage you to tune in. Also, we have just posted information about mock exam questions for all teachers, Kentucky students, teachers that want to partake. We are doing our own mock exam. You can administer those questions to your students. Then we are going to have a live scoring for our teachers. We'll be joined by Michael, as well as the College Board AP Calculus exam leader, Alex McAllister. So that should be a really exciting opportunity if you are interested in doing that. So check out kyap2020.com for more information on that. But if there's not anything else from you, Melanie, or Michael, we will go ahead and sign off.
All right. Thank you guys so much.
See you all next
Thank
week.
you.